The title of this presentation is Healthcare Systems Engineering. My name is Timothy Mattis. I'm an Associate Professor of Industrial Manufacturing and Systems Engineering at Texas Tech University. I put this presentation together a couple years ago when I was invited to give this talk down at Monterrey Tech in Mexico. And in particular, the purpose of this presentation is to look at the connection or the linkages between industrial engineering and healthcare systems. Some of that, again, is well explored, but I'm trying to present, or I will present in this presentation, a new look at that, right? Maybe try to look, how do these two disciplines connect? I'm also going to talk a little bit or provide some examples of projects that I've done which have used industrial engineering tools in a lot of different healthcare systems contexts, just to kind of get an idea of how the two, or how they can be used, how industrial engineering tools can be used in healthcare. And then also present some motivations for the healthcare systems, why now is the right time for these fields, and also some thoughts about future directions. Well, healthcare systems engineering is not new. Frank and Lillian Gilbreth, who are the pioneers of our field back in 1913, they performed time and motion studies, which again are bread and butter of industrial engineering, of surgical procedures. And then in the 1950s, Lillian Gilbreth used industrial engineering tools to address the nursing shortage following World War II. You can see here that the discipline gained steam throughout the 50s and 60s, and it became adopted into different associations of medical professionals and hospital management systems. I think it's interesting to look at how the name has evolved. That originally in the 1950s, it was hospital industrial engineering is how it was referred to. That progressed to hospital management engineering in the 60s, and today, and around the 80s, it changed to healthcare systems engineering. And currently, there has been a lot of recent interest in gaining popularity in this field. A lot of it, I'm going to talk about the motivation for that. But there was a journal that was formed by IIE, which is actually now IISE, which is the Institute of Industrial and Systems Engineering, a journal which is dedicated just to healthcare systems engineering. So it's kind of neat looking at these pictures here of the pioneers of our field working in different medical contexts. Now, healthcare systems engineering has been defined by the journal, the IISE Transactions Journal, as that healthcare systems engineering consists of the scientific study and application of innovative methods to improve the delivery of healthcare, or improve the value of healthcare delivery. And isn't that what we do in industrial engineering in general, right? I mean, we try to take a look at our knowledge of math and engineering and try to take that and combine it together to apply to real world problems, to make things better, to make things more efficient, to make things more safe. And that's really what industrial engineering is, right? Taking science and math and physics and applying it to real systems. And so healthcare systems engineering is nothing more than that application to healthcare contexts. Now, they also define in this journal different subdepartments. That is, when you submit a paper, there are these different subdepartments that you can submit to and who take up these different facets of it. And it's interesting to note that in their journal, they put the subdepartment as Healthcare Operations Management Engineering, Socio-Technical Systems Analysis, Quality Engineering, Healthcare Informatics, Medical Decision Making, and Healthcare Public Policy. And those are all good areas, and I can see why you would get lots of papers and why you organize around these different departments within the journal. But that doesn't necessarily make it clear, to me at least, the real linkage between industrial engineering and healthcare systems engineering. So for that reason, I tried to come up with a taxonomy that would try to take a look at what are the two different fields, how can we break them down, and then how can we connect them. And here's this taxonomy. So in industrial engineering, I could argue, and I think many of us could argue, that we look at products, processes, and people, right? That we look at how to be able to make a better product And within that field, we have our subdiscipline in industrial engineering of manufacturing, right? That's one of our areas of people who look at different manufacturing processes, different manufacturing methods, nano, 3D printing, lots of different manufacturing people who focus their research on improving the product. There's also people who focus on improving the process, right? That is operations research, and also systems engineering people fall into that too, I would say, where their objective is to how do I make that process more improvement, or how do I improve that process, the process that makes the products? How do I make it to where it's more efficient, more cost effective, more reliable? And then also people, which is the third facet. And that's where we get into human factors and ergonomics. How do people interface with different technologies? How do people interface with these processes and these products such that they're able to produce it, to do so safely, to not have failure, etc. And again, human factors and ergonomics. So I could argue, and I think many people would agree with this, that industrial engineering has these three different P's, or these three different facets. Now, what about healthcare systems engineering? Well, how can we connect those two? Well, I would argue also that healthcare systems engineering broadly could be broken down into patient care, patient flow, and patient safety. So have three P's of healthcare systems engineering, kind of like we have three P's of industrial engineering. In patient care, informatics becomes very important. How do we be able to interpret data to be able to improve the care of patients? Patient flow, take a look at logistics, inventory, etc. And then patient safety, looking at cognition, but also physical safety. A further breakdown shows that we have these disciplines again: informatics, logistics, and cognition slash safety, or cognition slash ergonomics, and then some applications, right? In informatics, one of the things that I've been looking at is these clinical decision support systems, medical sensors, devices. In logistics, again, you have inventory management, supply chains, capacity management. And then in patient safety and cognition, you got handoff management, infection control, medication management, etc. And all of the knowledge bases that you see down here of data analytics, statistics, Lean Six Sigma optimization, ergonomics, systems, etc., they all fall within, or those knowledge bases relate, and sometimes it relates to more than one, of course, but they all relate to these different aspects of healthcare systems engineering. So I'm not arguing that this is an exhaustive list, and you could maybe argue, well, what about this aspect of healthcare systems? Yeah, there's many more, right? There's probably, I'm not saying that this is exhaustive, but I think you could argue that you could break it down into these different focus areas broadly, and then from that subdivide a little bit more. So kind of come up with a taxonomy or a tree of how of what healthcare systems engineering is. Well, in healthcare, there is this this framework which is called the Triple Aim, and the Triple Aim was set up by the Institute of Healthcare Improvement. Many people who work in industrial engineering do not know the Triple Aim. They don't know of even what the Institute for Healthcare Improvement is. But the Triple Aim focuses, or the framework says, that projects or improvement efforts in healthcare has these three different facets. One being reducing the cost of care, the other one being to enhance the patient experience, and the other being to improve population health. That is, healthcare projects should focus on improving one of these areas, if not one or more of them, while not negatively impacting the others. And this is something that students in engineering often don't get, right? I mean, many times we teach our students how to look at problems and how to come up with optimal solutions, or how to improve a piece of the process without looking at how it affects the overall thing. And that's something that I think we should emphasize to our students, that all of the projects that they do, or even in us as professionals, that all of the projects that we do should be able to impact all of these areas positively, if not negatively, right? So again, we can come up with different solutions that per se would improve patient flow, right? That would make patients get in and out faster. But maybe if you're improving patient flow, it's costing more money, right? We're putting in different, or overstaffing, right? Or maybe vice versa. Maybe we have projects that improve the cost of care or make it cheaper, but it makes it, not as good a patient experience, etc., right? So we need to be sure that all the projects address these things and also comment on that in the projects themselves. And this slide I borrowed from Deloitte Consulting, and I think it was a really good one. I think what they do here is they talk about the different focus areas or the different resolution of the projects, where healthcare systems engineering research is either impacting the clinical aspect, which that directly aims to improve patient outcomes, or it has some non-clinical patient impact that it has benefits to the patient and caregiver, but they maybe aren't medical. Care delivery revenue and cost, that is going to make it make it cheaper, or provide more revenue to be able to use, or that it impacts the public as a whole or population health. So I think this is a value, because instead of thinking necessarily just about the different aspects or the different taxonomies of it, where are the projects targeted, right? That healthcare systems engineering projects don't always have to be targeted to just making a localized improvement in one particular facility that directly impacts the patient. That healthcare systems engineering has these broad focal areas of impact where each one kind of has a little bit of a greater resolution. So what are the motivations for healthcare systems engineering? Now, I point out about 3 or 4 of them in this presentation, but my argument is going to be that right now is really a time when healthcare systems engineering is a useful field, one which can make a large impact and make a big dent into many of the issues which are being experienced by the medical community today. Now, one of these motivation areas, which is very important, if not the largest motivation, is medical error. Medical error is estimated to be the 3rd leading cause of death in the United States. I've heard some people say the 2nd. I've heard some people say the 4th. It's very difficult to know exactly what that number is. Why? Because, of course, on death certificates, people don't write medical error as the cause of death for a patient. And so a lot of this is done by inference, trying to infer what happened. And also you have liability reasons and things like that. So it's not transparent necessarily what this number is. Now, I'm using the number that's well accepted, the one that comes from McAree and Daniel in the paper that they wrote in BMJ, which is an excellent journal. And they estimate that to be about 250,000 patients per year die due to medical error. And they point out in their paper that this is a very conservative estimate, that it's not even a liberal estimate, and it only is based on hospitals. It doesn't consider outpatient clinics, nursing homes, or other sources in which medical error can occur. And I use this slide, and I use it frequently, where we have the Boeing 747s, because each of those can hold, I think, roughly about 325 people. If you think about it, it would be really as if we took 2 Boeing 747s and loaded them up with people and then smashed them into the earth every single day, right? That's the number of people that are dying from medical error in our hospitals in the United States. If even one crash happened, it would make the news and it would be on there forever. For weeks, we'd hear about all the investigations that go into it. But when you put it in that context and you look at medical error, it's pervasive, right? That really, those are 2 plane crashes every single day. I believe that as industrial engineering, we can help in this aspect in trying to help avoid medical error, specifically looking at cognitive engineering and looking at different models for reducing medical error. Another motivation, this one is not is driven more just from the economies of the whole deal, or the economies of it, but our country, we are spending more as a percentage of GDP on healthcare than any other country. In fact, let me see if I can pull up my laser pointer here. I believe this is my laser pointer. You can see that here we are higher than everybody else, right? And I know this slide may be a little bit small, but here's the United States, and here's France, Sweden, Germany, Netherlands, right? And so they looked at the 11 most high-income countries, and as a percentage of GDP, we're 17%, and the next closest one is France at 11%. So, you would say, hey, that's okay. We spend more, but, we probably are getting better performances than those other countries. Well, that's not true, right? Here we are also not having the best performance. Neither is France, right? So France also doesn't seem to have very good performance scores either. So we're spending more, but we're performing lower than all of the other countries. And this, of course, is reported, I want to cite that, from the Commonwealth Fund in 2015, is from where this data was taken. And, of course, there are many reasons for that. It's not a very clear-cut answer why this is the case. But, obviously, just from the pure numbers, there's room for improvement, right? There is room for us to take a look at what we can do to help improve that. The next is electronic medical records. This is important from the availability side of things, that the transition to electronic medical records was a requirement of the Affordable Care Act, or Obamacare, that was put into place in 2011. I remember, just when I started in healthcare, when I started working in healthcare, maybe it was about 29 or 2009, maybe around there or so. And I remember the paper charts, right? And you'd have the unit clerks and that. But now everything is moving to electronic medical records. Now, I know that transition has been lengthy, and some people argue. In fact, I give other presentations where I talk about we need to re-envision how we actually collect this medical error, because we don't want for the information technology to become a burden on the providers. However, the EMRs do provide a source of data that is useful for mining and analytics. If we can get past a lot of the medical and hurdles and get past, patient privacy things, we as industrial engineers have a rich source of data that we can mine and that we can look for patterns that we can run tests on and try to improve, again, these metrics of care, flow, and safety. So having this new resource come about in 2011, which surprisingly, that's at the same time the journal came out, gives us much more ability to use our knowledge to improve healthcare. Another one is value-based reimbursements per patient care. In 2018, 90% of Medicare payments were to be tied to quality, and by 2020, 75% of the plans will be value-based. That was from the Department of Health and Human Services, what they published in 2015. In essence, for those who aren't familiar with it, that before reimbursements were tied to a fee for service, that as long as providers were providing a service, as long as they were providing a service, they would be reimbursed for that service. But now it's as if they get reimbursed only part of what they would get reimbursed. So instead of getting everything back, they get a portion of what they would have got back, maybe say 90% of it. But the remaining 10%, they're going to need to show that they're delivering value in their care, that they're just not treating and releasing, but that they're caring for the patient and they're looking more at their overall medical condition. And then they can get even more than 100%, maybe get that 105% to where there's incentives built in. So value-based reimbursements or reimbursement models have the ability to be a double-edged sword. It can be a negative impact for a healthcare facility, but it also could be a positive impact. So there's a big opportunity here for us as industrial engineers to be able to try to improve or work on these programs to how to deliver value and how to deliver comprehensive care to the patient population of a clinic and or healthcare facility. Now, what I want to do in this presentation at this point is to just go over a sampling of some of the projects that I've been involved with in the past. The only intention for doing this is not to be like, oh, look at me or look at the things I've done, but rather just to give an idea of, from my perspective, some of the things I have done, and maybe this will help you as a healthcare professional or as an industrial engineer think of different ways of which you can build off of these or go in different directions, or at least give some ideas for how industrial engineers, myself, have worked with healthcare professionals in the past, and to how I've utilized some of my knowledge from industrial engineering to make improvements in healthcare. The first project is on healthcare readmissions. This one, the motivation, healthcare or Medicare will not reimburse hospital admissions within 30 days of discharge for complications that resulted from the care received. It's estimated by, I think, by CMMS that 1 out of every 5 Medicare patients is readmitted within 30 days, and these accrue a cost of $17.5 billion per year, right? In fact, this is when there was at one time where this was a very important, at a hospital that I was working with, a very important thing or a very important issue that they were working on. And so some of the questions that were asked are, what are the primary predictors of patient readmission, right? Are we able to identify which of these patients are going to be readmitted, both looking at their medical or the clinical side of things, but also the social side of things, the socio side of things? Hey, can we be able to come up with some sort of way to identify early who these patients might be and then build interventions around these? Also, they had a LACE tool that they were using to do this, and part of it is this tool any effective? And one, were they using it right? And two, even if they were using it right, was it doing anything better than just throwing a dartboard? And there were some very interesting things that we developed through this project, or many interesting things that we've seen, some of which there's a book about healthcare engineering problems. It's by Kolker, and one of the things he talked about was machine learning to try to cluster people and cluster groups together, and that's actually what we did in part of the things that we did in this project. So we had to use analytics, we used some logistic regression, we used other forms of machine learning and clustering to try to discover what these correlations were. First testing the LACE tool, but then also trying to figure out, can we group patients together, and then what are we grouping them by, and how can we determine what the intervention should be. And in this project there was a whole team of nurses that was assembled to address this and provide interventions to try to reduce the rate of hospital readmissions. Whoops. The second project is on radiology workflow, or a second project, not the second project in time-wise, but just second project I'm presenting, was radiology workflow. The radiology scans are frequently ordered in the emergency department and on the floor in a course of care, but they were a bottleneck in the sense that the scans were not seemingly to be done in an efficient time. And this became very frustrating. So how could they reduce this bottleneck? And so the questions are, why is this a bottleneck, right? What are the factors which are making this? You know, some of the scans as you see in this, or some of the devices, the x-ray devices you see here were the portable ones that an x-ray technician could push around. Some of them they had to go to the actual x-ray rooms. So you had different types of x-rays or different types of radiology labs, but where were these portable machines? Where were they stationed? You know, how were they being summoned? They were trying to invest in different forms of technology to be able to get the scans faster into the system, but were these justified? Is the problem the technology, or is the problem the design of the system around the technology? Generally, one of the things that we do I guess maybe one of the things in industrial engineering, and one of the main tenets of process improvement, of course, is first reducing variability before trying to improve the mean, or first looking at the system before trying to make a local improvement. And so was technology really the answer or the issue here? In doing this project, there were many tools of industrial engineering. A lot of them, this again was a big data problem. There's lots and lots and lots of data. But one of it was trying to find these outliers, right? Where are the outliers? And trying to make sense of the outliers and understand, okay, well, what's causing these large deviations? And then is that really something which is, just a rare exception, or is that something which translates to others? Are those by understanding that root cause, will that lead us to the bottleneck? And again, another really fun project. Another project that we took a look at was slips and falls. I didn't know at the time when I started this project just how prevalent a problem this was. Not only how prevalent it was in the sense of the patient population, but also the financial impact. That I guess from a paper that was written in 2008, it was noted that the probability of an inpatient fall is 1 to 3% across all hospital admissions, and these account for 90,000 serious injuries and 11,000 fatalities on average per year. As these patients fall, it's considered to be an avoidable accident. So the hospital does not get readmission or does not get reimbursement for this. And these falls, especially in the elderly population and other populations, can account for a significant amount of time that patients are in the hospital. And when we looked at the economics of it, it actually has a very large economic impact. So there were some scales, in particular the Morse Fall scale, and different tools that were being used to try to determine the probability that a person would slip and fall. But then again, the question is, are these valuable? One, are these tools being used the way that they were supposed to be used? That was the first thing. And then even if it was, is it something which has predictive power? What factors are contributing to the slips and falls? And in particular, one of the things that this hospital was trying to look at is putting high-risk patients near the nursing station. Is that going to make a difference? There's also the issue of bed alarms that come in here. Do bed alarms, alarm fatigue? So those are human factors and human-computer interaction issues that come in. I didn't note that here. I guess I did with cognition. But also the ergonomics, some IE tools, and I had to go talk to some of my ergonomic buddies who actually studied this coefficient of slips and falls, and but slipperiness of the floors. Are there physical interventions? Cognition on I talked about bed alarms, but how can we make people more aware of that they're going to slip and fall, or that they have a high potential for that? And I have some, personal stories on that, and I don't want to delve off into personal issues here, but I do. I had a loved one in the hospital who turns out had a head injury, and the bed alarm wasn't working because it wasn't plugged into the wall, and she got up and had urinated because she didn't know where she was at. She had a head injury, a brain bleed, and she slipped and fell. And so there was a whole series of events that led up to that. And again, she was in the hospital for a few more days. But again, that was avoidable. And you can think of several different interventions which could have been done to have made that never happen. Also, some other IE tools, obviously descriptive statistics. We also did a little bit of Bayesian analysis in there because unlike the other, we didn't have a lot of data here. So we were trying to do the best we could with limited amounts of data. Discharge plan and scheduling. This was actually one of the very first projects that I ever did. But that, as in many times in many hospitals, there's a backup in the emergency department where patients are getting stuck and they're not able to flow in. And the question is, why was that, right? Is it that the patients weren't getting out? Is it because the beds were being hidden? Is it why was it that there was such a discharge or such a backup? And so we took a look at this, and the discharge policies in many hospitals too is quite common to get people out by noon. Okay, I understand that. So that's a good thing. But people don't come in around noon. You have spikes of admissions. It's not like you have everybody trying to come in before noon when they're trying to get everybody out. And even if you set that metric of trying to get out by noon, are you designing your processes to make that happen? Because most of the time, the patients, they want to get them out by noon, but the labs aren't getting there in time. There's labs being ordered. The physicians aren't rounding then. They haven't made accommodations for where the patient's going to go. There are a whole lot of reasons why patients weren't being discharged. And so one of the things that we were trying to look at is, can we plan this better? Can we do better at trying to figure out how to get patients out of the hospital? In fact, we even tried to come up with target times and tried to design, set target times and design processes around that. Again, one of the tools, optimization, was very big here, mixed integer modeling, systems modeling, programming. I had to learn a whole lot, not I, but other people on the team had to learn a whole lot about programming and writing in Excel. We were so used to writing in CPLEX, which for those of you in healthcare that may be viewing this, CPLEX is a programming language used in industrial engineering for solving optimization problems, which is very expensive. And so at the hospital, they didn't, there was way too much money for them to put up for that. And plus, it didn't interface. So I had to learn a lot about Excel and Visual Basic and how to get the two to talk together. And then also scheduling. A lot of this was looking at dispatching rules and scheduling. Another project was on compliance and care bundles. That for medical procedures, there are often 4 to 6, so maybe more, maybe less, but different care items which are supposed to be done at every procedure. And these have been developed, these 6 or so specific items have been developed by experts in the area. And so in monitoring this, many times people use Shewhart control charts. But Shewhart control charts are not able to capture this very well. Shewhart control charts are meant for normal data. It's not meant for probabilities, and this is actually what's called the J binomial distribution or the Poisson binomial distribution. So we try to develop a control chart around the J binomial distribution. If you do that exactly, because it does have an exact probability mass function, you can do it, but it may not be computationally feasible because it's a very large, to enumerate all the possibilities would take a while. So we used some IE tools. We used control charting, looked at probability limits, and we also looked at probability generating functions as a means to calculate these probabilities by just expanding polynomials and picking off coefficients instead of having to go through and actually do large amounts of computations like combinatorial style and evaluating the PDF of that Poisson binomial distribution or the PMF of the Poisson binomial. So yeah, it took a lot of the tools that we learn in probability course and also in quality control. Another project was on the emergency department workflows and labs. In this, the emergency department was experiencing really long wait times for patients trying to come and being seen, and it was noted that a lot of times the patients are sitting in the rooms back in the emergency just waiting for the labs to be run. And so there was a question of exactly where's the bottleneck, right? Is it in the lab? Is the lab causing the delay? Is it the emergency department that's causing the delay? Or is it the handoff between the lab and the emergency department and the delay, right? So it's identified roughly that labs was it, but it wasn't exactly sure where it was or what the cause of that bottleneck was. So how could we redesign the workflow? And where should we redesign the workflow? And could we use like standing orders and things like that? Or would using standing orders have made a difference in loosening the bottleneck? So these were some of the questions that we addressed in this project. Again, statistics was used, the idea of using statistics and simulation, discrete event simulation to come up with some big models to try to evaluate the impact of different procedural changes on how those would actually draw, or where the bottleneck is, or where the bottleneck might be in the models, and then how reducing those might impact the overall flow. And then also using some operations management, looking at workflow redesign mechanisms. Another project was on patient safety. Medical error, again, as we've talked about, is a third leading cause of death. So one of the issues was, how can a hospital measure whether or not it is implementing a culture of safety, or whether or not it is safe? Now there are different surveys which are out there, of course. One of them being put together by AHRQ. I think it's called the Patient Satisfaction Score. I can't remember now at this point in time, but there are ones that are out there, but they don't necessarily, as we looked into it, they don't necessarily measure safety in the sense of avoiding large errors. They were looking more at safety in the new thing. A lot of times the compliance standards are like JCO and that are more looking at specific, whether you're meeting specific adherence criterion, but it doesn't really look at that culture of safety and safety culture. So trying to figure out, how can we measure that? And we got into a lot of things in cognitive engineering, looking at cognitive dissonance and cognitive traps and blunders, systems modeling, really taking a look at handoffs, and then also statistics, having to design survey instruments using Likert scales, et cetera, to measure what really is the safety culture. Insurance eligibility. This was a project where we were trying to look at how to be able to help more people become eligible for insurance benefits. Texas has the second highest uninsured rate in the United States. This comes from the Texas Medical Association and the Commonwealth Fund. And it's very well known that if you do not have insurance, then generally your health status is not nearly as good. And this is an interesting graphic over here, looking at the percentage of adults that are uninsured. You can see that Texas here leads. I think this is Florida, New York, and California, and here's the U.S. total. So you can see that Texas, we're underperforming when it comes to providing insurance. I think Alabama was the state that was the only state that was actually worse than us in this metric. So what are those barriers, right? Why are people not seeking eligibility for government programs? Do they not qualify? Do they qualify but they don't know they don't qualify? Do the providers not know of, are there things that we're missing? Are there ways that we can get people to identify themselves, especially for their children, right? In the cases, can we get children on Medicare or other government programs to be able to help individuals be able to receive care? So that was the other question that we were trying to answer, is how can we design a process? Can we help a clinic? Can we design a process with the clinic to be able to help them to assist individuals in becoming aware and becoming eligible for coverage? Some of the IE tools, value stream mapping, right? The big one that we learn when we do our basics. Many students learn in their basics IE courses about value stream mapping, just basic production and basic quality control. Also Kaizen events, right? In this particular case, we tried to use Kaizen events to be able to come up with process improvements. Another project was on value-based reimbursements. Again, as we talked about previously, that many of the insurance companies are moving towards value-based care in the sense that to get full reimbursement, you're going to need to show value. And also the Department of Health and Human Services, or the Human Resource and Services, HRSA, for the FHQCs, Federally Qualified Health Centers, they have these quality improvement awards. And one of the things that we were looking at is how can we help this clinic be able to achieve these quality improvement awards. And so how could we identify, right? Where are the gaps? So they have several different, for those of you familiar, there are several different aspects of these quality improvement awards. There's several different actions that are measured by HRSA, which looking at, for example, do they manage a person's diabetes? Are people in the patient population, their diabetes being managed? Is their weight being managed? Are they educated about smoking cessation, et cetera? There's all these different categories. So how can we identify these patients in the population that are not receiving these services so we can give them these services? How can we get providers to be able to notice, hey, there's a patient that's coming in, let's do this to be able to, let's be sure that the next time they come in, we're able to check their diabetes or get their A1C scores, et cetera. So how can we identify these patients? How can we get the providers to do this or to work with these patients, and a lot of things come into this. A lot of IE tools, scheduling. I didn't write that here, but scheduling is the big one. Another thing is just programming, having to get into these EHR databases and pull out data, and then also feed data back in, right? So get data out, feed data, and then also data visualization. There's such massive amounts of data. I forget exactly, but there's so many visits that were being seen that it's very difficult to just get your head around it. So you also had to look at big data techniques and how to visualize big data. And so you can find those patterns and communicate those patterns to the providers. So now moving away from the different projects that have been done, want to get back to just talking about healthcare systems engineering and some of the barriers that I see to healthcare systems engineering and industrial engineers working in this field. And simply, I guess to say it as succinctly as possible, that most industrial engineers just simply do not understand the realities, the complexity, mission, and culture, and that's what I mean by the realities, of healthcare organizations, which limits the usefulness of healthcare systems engineering research in present day. I think that even people who I know that are very seasoned industrial engineers still continue to treat a hospital like a manufacturing plant, where you're treating, doctors are machines, patients are parts, and things should just flow around. Let's make this work. And they don't understand the complexity that goes on every single day, in both the complexity within the organization itself, the mission of of a healthcare organization, and the culture. So to elaborate on that, IEs in general, we think in terms of productivity, but healthcare thinks in terms of liability. And maybe I don't mean that in a harsh way, but we don't think in terms of liability in industrial engineering. We just think about how can we make the process more efficient. There's none of this, there's no concern of necessarily who's going to be held liable if something goes wrong. Basically, in a production system what's going on. But in healthcare, liability is a big issue, right? The doctor, the communication with the patient, what is appropriate to communicate? Who is it appropriate to communicate? What can be communicated by who? Who makes the ultimate decision? Who's held liable if something goes wrong? If that person's held liable, then they want to have probably more control over the decision making than a hospital administrator would, right? A hospital administrator isn't necessarily going to bear the consequences for a medical error that occurs. So liability is a huge concern. And that's something that IEs don't necessarily consider when they're trying to design process improvement techniques. Healthcare has many different forms of delivery. Most of the time, we talk about hospitals, or I do, because it's just simple. But actually, I've done a lot of work also in outpatient clinics and health centers. And the culture in a hospital and their mission is extremely different than it is in an outpatient clinic. The hours they work, the connection they have with the patient. And then there's other, mental health facilities, senior care facilities. Healthcare has many, many different forms in and of itself. We're not even talking now about how it interfaces with the government or necessarily how it interfaces with insurance. But just in and of itself, there are many, many different, when you say healthcare, that can mean many different things to many different people, and it encompasses a huge body. So again, people I think in engineering don't necessarily see that. In fact, I would say most people, when they say healthcare, they just immediately think about a hospital, or they think about their primary care provider, but they don't really think about all these different aspects and how it might be different in those different delivery modes. Also, there's many different actors with diverse levels of education, pay, and liability, right? And you have all sorts of different providers, physicians, PAs, residents, nurse pracs, different levels of nursing, transporters, billing. Each of these people have different responsibility levels, different liability levels, different pay levels. And so when you're designing interventions, when you say, okay, well, I think we should add a nurse, well, what type of nurse, right? What skills does that nurse need to have? Are you talking about we need to add a LVN or we need to add an RN, right? These things, which if you're listening to this and you're a healthcare professional, you're probably like, well, no duh. But if you're listening to this and you're an industrial engineer, you may be like, well, What is the difference? Why can't they all do the same thing? Or what's the difference between a physician and a resident? And why do the residents have to meet with a physician every day at 2 o'clock, et cetera, right? Things like that. And how might that impact patient flow, right? There's these complexities that are going on based on all these different actors and all their different modes. So it's not just, a nurse is not just a nurse, a provider is not just a provider. And those subtleties are things that aren't often captured by engineers. And this is one which I think is a big one, that healthcare organizations are complex adaptive systems, not traditional systems. This is a recognition of people who work in systems engineering in the industrial engineering field, that if you were to talk to somebody who works as a systems engineer, they would say, oh, of course, I know what you're talking about. But if you talk to people who work in operations research or other parts, they may not even really understand, well, what does it mean a complex adaptive system? How is that different from a traditional system? Right? In complex adaptive systems, we look for emergence. We look for emergent phenomena. How do things emerge from localized interactions? Because the system is a living system, even though it may be an organization, the organization is an organism which is growing and learning and emerging, and these complex local interactions lead to big system events. What we see, where traditional systems are the cause and effect type systems, right? So we don't talk about emergence, we talk about cause and effect. There's an effect, what's the cause? Right? Let's engineer a barrier on the cause to keep the effect from happening. In a complex adaptive system, barriers aren't that useful because it's going to be changing. The barrier one day may not be the barrier the next. And so many people in engineering address a healthcare system as a traditional system, looking for cause and effects. And what they don't realize is that because of the complexities, because it's a humanistic system, because there's so many non-technical parts to the system that go on, it's really a complex adaptive system. So trying to just find a solution to the problem or find the cause and effect and engineering a barrier isn't going to be the right approach. And in fact, there's many papers out there, I haven't cited them here, but there's many different papers out there that talk about if you try to implement cause and effect or engineered barriers on complex systems, you're causing more complexity, which means it's just going to end up causing more errors and more faults and more bottlenecks and more delays. And that's been the approach, unfortunately, I believe, for a long time, is just one program after another. Right? Let's come up with another new program to fix this cause. Let's fix this cause. Let's fix this cause. And in reality, it just keeps making the problems worse, and nothing's getting better. So that recognition is something that many industrial engineers do not make. So even more than that, I guess it could be summed up that the common fallacy is that patients are not parts, providers are not machines, and hospitals are not factories. We often work in this world right here, right? Where you're working in a factory, you have some sort of sub-assemblies, assemblies, parts flowing in, flowing out, storehouses, warehouses, very regular, like clockwork. You can manipulate it, move it, whatever. But this is a reality of what's going on in healthcare. You have people coming in and out. You have people who are waiting. They may show up on time. They maybe don't. They may be sick and tired, and they're not in good moods. A lot of things go on. And if we make a recognition that we're not dealing with this, but we're dealing with this, the approaches that we're going to use are going to change. And that's often that's uncomfortable because we don't like change, right? We know how to make this, but we have to change and think a little bit about what can we do to address the problems here that are happening in healthcare. Another common fallacy is that the overriding goal of any healthcare organization is to provide the best patient care possible. In fact, if you were to, dare say, talk to any provider of healthcare in the medical world, and you were to say, what is your mission? It would be, well, the mission is to provide the best patient care possible, right? We don't look at the person. We don't look at not look at the person in that regard. We don't make judgments. We provide the best patient care to everybody who we can. And our only mission is to be sure that that patient gets healed and that that patient comes out of there better than they came in. And then that's part of the oath that is taken, right? It's not to be an efficient system, right? The overriding goal of any healthcare organization is not to be an efficient system. And many times industrial engineers just don't get that, right? Why? Because again, it goes back to that manufacturing metaphor. There we want to produce quality products, but we're always looking to make efficiency, efficient. But we don't look at that. It's hard for people in engineering to understand that the mission of a healthcare organization is not necessarily to be efficient. They want to be efficient, right? It's not that they don't want to be efficient, but their goal is not efficiency. And so as we look at these projects and as you look at these healthcare problems, it needs to go again kind of also to that triple aim type thought. That how do the projects meet the goal of the healthcare organization, which is to provide the best patient care possible? And lots of things go into that. Having efficient care is good patient care, right? Having people be able to not pay a lot is best patient care, right? So that doesn't necessarily mean that best patient care means it costs more money or time. What it means is that the goal is to provide that, with efficiency being a desired effect or side effect. And finally, some of the things for educating healthcare systems engineers, I believe that we need to introduce industrial engineers to systems theory. Again, this builds on the slides that I was just saying. To work in healthcare, need to really have an understanding of what is systems theory, what are feedback loops, what are causality loops, what are nonlinear effects, etc. Teach IEs about the complete data analysis process. This is probably true many times, but a lot of times as industrial engineers, we just kind of jump in here right at building the model, generating results, maybe validate results, hopefully, right? At least we kind of do some of this right here, but we often don't really look at these parts. Cleaning the data, exploring the data, visualizing the data, mining the data, right? These are things which are kind of more of emergent fields, but ones that need to be looked at, because if we just jump to building models and generating solutions, many times we're going to be missing the mark. So that would be another thing to be able to revise our curriculum and revise our programs to do the full data analysis process. Another is immerse IEs in a healthcare environment. This is something which I feel is critical, that to be able to do effective research in healthcare, you need to be in healthcare, right? That it's going to be extremely difficult to be able to make improvements in a healthcare setting if you're not immersed in that healthcare setting. And I believe this goes both ways. I know that many times I've asked people, like, well, I'd like to see, when I work on consulting projects or just research projects in general, I like to see what I'm doing, right? I can generally, if I understand the system, I can make a solution. But if I don't understand the system, I can't. And there have been times I've asked people and I've said, hey, I'd like to just be able to have a pass, to be able to see what goes on. And often that's very difficult to get, right? It's difficult to get, and it always is difficult, right? There has to be an element of trust and all that there. But to be able to really make an impact in healthcare, industrial engineers need to be in healthcare, right? Need to have close collaborations, need to be at the hospitals, be at the clinics, be at the mental health facilities, walking around, looking, trying to be able to conceptualize what's going on there to be able to help apply the tools that they have. Also developing postgraduate certification programs. I believe that there's more of these coming about as time goes on, but many times there aren't this. So graduates come and they want to work in healthcare, but they don't have necessarily the certificates or the qualifications to. By developing these programs, it would get people into these healthcare organizations. It would start teaching them about the intricacies of healthcare systems so they're better able to apply the industrial engineering tools that they have. So in conclusion, there is a need for educational research and professionals in healthcare systems engineering. I believe that there is clear motivation for this and there is a dire need for it. I believe that under the taxonomy that was presented, that just as we have 3 Ps and IEs of people, product, and processes, You can translate that to the 3 Ps of healthcare systems engineering and patient care, flow, and safety. Healthcare organizations are complex adaptive systems. They're not traditional systems. That's something that needs to be considered when trying to look at interventions. And similar to learning a new language, IEs must be immersed in healthcare to become fluent and to make an impact. So that's my presentation. I appreciate your time and attention.